We are living in one of the great ages of bridge building, with engineers creating higher, longer and more spectacular structures than ever before. They defy gravity and reach out across great divides. Driving across them, we take them for granted. But when bridges go wrong, the consequences are appalling.
It looked like a war. There's people screaming everywhere, blood, cars sinking, people in them.
And it shakes our faith in the world.
I mean, I still sometimes am trying to wrap my head around why I'm alive still, because I thought I was dead.
Now, bridge builders must ensure that these modern marvels don't fall prey to the disasters of the past. They go back to those disasters and examine them forensically, like a detective at a crime scene. Previous mistakes are analysed and new technologies devised to combat past failures. In short, every major bridge under construction is being built from disaster. Bridges showcase some of the most awe-inspiring engineering on the planet. Engineers can now build bridges of astonishing height, length and beauty, and designers try to outdo each other with the boldness of their creations. But increased ambition means overcoming increased risk. And when they don't get it right, the results are catastrophic. In 1940, the Tacoma Narrows Bridge in Washington State was ripped apart by the wind. In 1970, a bridge in Australia collapsed during construction, killing 35 workers. In 1980, the Sunshine Skyway Bridge in Florida was destroyed by a freighter, plunging traffic into the water. And as recently as 2007, an interstate bridge in Minneapolis suddenly collapsed, claiming 13 lives.
Bridges are not supposed to fall, and there's not supposed to be a collapse like this.
When bridges collapse, engineers have a gruesome blueprint of what went wrong and learn vital lessons from those failures. This means that new bridges, however bold in design, will be disaster-proof. One of the most ambitious bridges in the world is Stonecutters Bridge, currently under construction in Hong Kong. When completed in 2009, this stunning super bridge will be the second longest bridge of its kind, with a main span of over 1 kilometre. Stonecutters will span the entrance to the world's busiest container port and will allow cargo to be moved rapidly in and out of mainland China, providing a vital artery for the country's expanding economy. The bridge is also intended to create a monumental addition to Hong Kong's ever-changing skyline.
Many cities worldwide are identified by their bridges, such as the Golden Gate Bridge in San Francisco, the Tower Bridge in London, Sydney Harbour Bridge. Stonecutters Bridge will achieve similar iconic status when it's completed.
But the engineers behind this Golden Gate of the East have more on their minds than just function and beauty. They also have to build against a whole range of disasters which could befall a bridge of this kind. They have to worry about the complex aerodynamic environment of the surrounding terrain, protect against the corrosive nature of the salty air, prepare for the onslaught of the annual typhoon winds, and plan for the threat of being hit by giant container ships. No one expects a bridge to fail. But when it does so with spectacular and catastrophic consequences. This is Minneapolis in the American Midwest, on the banks of the Mississippi River. On August 1st, 2007, it became the site of one of the most shocking engineering failures in American history. At 6:05 that evening, Lindsay Peterson was driving home from work across the Interstate 35 West Bridge.
I usually took that route. I mean, it was very common for me to take 35. My job is right off of 35, and my home is right off of 35.
Lindsay found herself in slow-moving traffic in the middle of the bridge when there was a sudden noise.
I actually heard this really distinct sound of metal snapping. And within seconds after that, I was falling.
The bridge had given way beneath her.
I thought that I was gonna die as soon as I landed. I thought I would land on the cement or something and it would smash me like a pancake.
There was a team of construction workers on the bridge at the time of the collapse. Nothing alerted them to what was about to happen.
I was moving a piece of equipment and the bridge started to shake. which it normally does when a heavy semi goes across or whatever, and it shook, and then all of a sudden it just fell out from underneath us.
Jeff was driving an earth mover when he fell more than 30 meters.
I mean, there wasn't really anything you could do, or nowhere to go. You couldn't run or do anything. So I bounced off the piece of equipment that I was on and then cartwheeled off into the water.
Stage by stage, the bridge was collapsing.
The north end of the bridge buckled up 40, 50 feet in the air, slab by slab, like a snake, coming right at me. And it just looked like a monster, the way it took cars, and it would buckle up and cars would be suspended in the air and then come back down on the bridge. And when it got to me, it lifted me up, and then 1-2 seconds later, the whole bridge just went down. And I remember screaming out loud, "No, no, no," and I truly thought that was the day I was gonna die.
Andy's car fell 15 meters, but stayed on the wreckage. Lindsay Peterson's car, however, went straight to the bottom of the Mississippi River, with Lindsay still at the wheel. In August 2007, the I-35 West Bridge in Minneapolis fell out of the sky without warning, throwing cars and people into the Mississippi River.
I was instantly submerged under the water. The water was there right away. I didn't have even this moment to gasp for one last breath of air to sustain me.
Lindsay became disorientated in the murky waters and couldn't find a way out of her car. But construction worker Jeff Ringate managed to swim to a piece of debris.
There's people screaming everywhere, blood and cars sinking, people in them, and rubble and rebar sticking everywhere. It looked like a war zone.
Jeff caught sight of Lindsay and knew he had to act fast.
She was in bad shape. She was in the water. Me and my buddy Josh pulled her out with a broom handle, and she was bleeding and broken back. She was in bad shape.
I don't know how I got out of my car. It's really a mystery. The only clue that I really have is that my fist is filled with scars. It looked like I had punched a window. I don't remember punching a window, though. I would think that I would remember having superhuman strength like that.
Andy Gannon still has nightmares because of what he saw.
The vision of the buckling is what I have the hardest time forgetting. I just can't believe it happened.
These were the lucky ones. 13 people died and many more suffered serious injuries. The nation was stunned. How could an ordinary interstate bridge suddenly fall out of the sky? The area was cordoned off like a crime scene, and investigators combed the wreckage for clues. Even veteran bridge experts were shocked.
It was exactly the same reaction that I had when the World Trade Center collapsed. I said, this can't happen.
The incident at Minneapolis scandalized America and severely damaged trust in the country's infrastructure. The I-35 bridge was a 40-year-old steel-deck truss bridge. There are 465 similar bridges across the USA. How many others could collapse?
You can't live in Minneapolis without going over a bridge. It's pretty much inevitable. I just kind of have lost a trust in the world.
The inquiry into why the bridge failed is still ongoing, but various theories have emerged. One theory points to a possible design failure. The bridge stood on 4 central piers in the river, and initial inspections have suggested that there might have been an inherent weakness in the plates which held the structure together at these 4 points. It's believed that the gusset plates were half an inch too thin for the load-bearing needs of the bridge. But it wasn't clear whether the mistake had occurred during the design or construction of the bridge. Professor Ted Galambos has studied the history of the bridge.
The bridge was built exactly as it was designed. So the designer specified this thickness for these plates. Why he did this, we will never know, because the person who did the design is long gone and dead, so we can only guess.
So was it basic human error? Did the designer get his calculations wrong?
I think the more likely scenario is that the designer thought it was going to be a different strength steel that was going to go into that joint.
The bridge was built during the American construction boom of the 1960s, and there was a drive to save money by using lower-grade steel. In the I-35 bridge, there was a mix of different steels in the gusset plates.
In structural engineering, you have a constant battle between economy and safety.
Despite the alleged design fault, the bridge stood for 40 years, so why did it suddenly fail? Over time, metal suffers fatigue cracking through repeated stress. It's been estimated that the I-35 was pounded by 17 million trucks during its lifetime. Exposure to the elements also makes bridges victims of corrosion, which eats away at the metal structure. Minneapolis has the most extreme temperature swings of any city in the United States. In winter, temperatures can plummet to minus 30 degrees Fahrenheit. De-icing systems had been in place on the bridge for several years using potentially corrosive chemicals. By contrast, on the day of the collapse, the temperature was a sweltering 100 degrees Fahrenheit, which would cause the metal structure to expand. In addition, the bridge was undergoing repair work, and the contractors had equipment and materials on the bridge, adding extra load.
I'd been there about 3 weeks. I was underneath it. It was in bad condition.
If the structure had faulty gusset plates, then wear and tear, extra loading and extreme heat could have tipped it over the edge into sudden and massive failure. Furthermore, some experts pointed out that these problems might have been picked up on if the bridge had been more effectively monitored. Emergency tests have been carried out on the 465 similar bridges across America, which might also be vulnerable to collapse. And the bridge builders of the future will need to learn valuable lessons from what happened on the I-35. And in the era of super bridges, failing to learn these lessons could lead to catastrophe on an altogether different scale. Stonecutters Bridge in Hong Kong is one such super bridge. Its magnificent 1 kilometre span will be exposed to everything Mother Nature can throw at it. Standing at the gateway to the South China Sea, it will have to tolerate an exceptionally humid and corrosive environment.
We are in a marine environment, and that brings it with extensive and heavy chloride presence in the atmosphere around the bridge.
To fight corrosion, the engineers are using super durable materials.
We've put a stainless steel top to the tower. This reduces considerably any maintenance at the top of the tower.
The stainless steel skin is of a super high grade and was fabricated in the UK. It'll provide an impermeable layer of resistance to the elements and will never need painting. The concrete used in the bridge is also of a particularly high density to stop chloride penetration. If chloride from salt water gets into the interior of the structure, the steel will corrode and then expand and then crack the concrete. To protect the deck, the inside will be fitted with dehumidifiers to reduce the corrosive atmosphere. For the bridge builders in Hong Kong, the collapse in Minneapolis has sent a strong and clear message.
The bridge collapse in Minneapolis highlighted the importance of a good maintenance regime for any bridges throughout the world. And maintenance of structures is absolutely vital.
The design of Stonecutters includes a variety of innovations for inspecting and maintaining the structure throughout its life. There will be retractable inspection gantries at the top of each of the towers. There will even be a maintenance shuttle train inside the deck to help monitor the interior of the bridge. And it's not just the bridge that needs to be protected from the elements, it's also the staggeringly high approach roads, which will bring up trucks from the nearby container base. Because Stonecutters is more than just a bridge, it's a vital link in a whole infrastructure chain of roads, tunnels and causeways. And its creators need to make sure that it stays corrosion-free for at least 60 years. Back in America, this kind of innovative approach to durability and safety is now being applied in Minneapolis, where bridge builders are working round the clock to replace the fallen I-35. And the new bridge has to prove itself to a suspicious public. For John Chiglow, it's a tough call.
Bridges are not supposed to fall, and there's not supposed to be a collapse like this. And so we have to reestablish that trust and confidence that when people use these facilities, they can use it and use it safely. We've been working around the clock since then, 24 hours a day, 7 days a week. There are no holidays on this job.
Incredibly, the plan is to complete the new bridge within a year. The I-35 is a vital road artery running from Texas to the Canadian border, and it needs to be fixed quickly.
We've estimated that each day this bridge is out of service, there's a $400,000 a day impact to the traveling public. That does not include the impacts to the businesses. That that's what really justified approaching this project in this aggressive of a time frame.
To speed up the process, the contractors are using a system known as design-build, in which construction starts before all elements of the design have been finalized.
One of the unique elements of this construction is particular parts of the job continuously going along at the same time as others are being designed. We work at the bottom when we have not yet got what sits on top of it designed, and continuing we work at the piers, whereas we didn't have the design of the deck finalized, and all the way along. We know the order we're going to build things, so that was the same order that we had things designed.
But the speed with which the new bridge is being built has also raised concerns.
Immediately after the collapse of the previous structure, there was initial concerns when we announced the schedule that we anticipated this bridge being built in regarding safety and how we were going to ensure a high-quality structure.
The man responsible for making design decisions during the fast construction process and for ensuring that the bridge is totally safe is Christopher Burgess.
This bridge is a very stout structure. It's one of the stoutest bridges that I've ever designed and worked on. We are now inside the bridge, directly underneath the roadway deck. You can see here the post-tensioning strand that hold up this span. Each one of these cables right here hold up 1 million pounds worth of tensional force to compress the span.
The new bridge is made out of precast concrete segments known as box girders, and these are held up by a combination of vertical piers and steel cables, which run through the girders, compressing and anchoring the structure. Unlike the old bridge, the new bridge has multiple levels of structural redundancy built into it. In engineering terms, this means that if one or even two elements fail, the bridge will still stand. It's a belt and braces approach to safety.
Also inherent in the design is a great deal of repetition and redundant features to avoid any potential issues that happened with the older structure.
The bridge is in fact two bridges, one northbound, one southbound, with two hollow box girders in each direction.
Each box girder is resting on its own pier. Each set of piers is resting in its own foundation. Separate structures, northbound and southbound, are separated by 8 feet. With that separation, one doesn't affect the other. There are many, many post-tensioning strand cables embedded in the bridge. If any one particular cable shows distress, it doesn't mean collapse or failure of the structure. So there's many features to make the structure as redundant as possible. In other words, you make as many possible chances for loads to get down to the foundation.
Unlike the old bridge, the new I-35 will have no Achilles heel, no single point where it could fail and bring the whole structure crashing down. In addition to all the redundant features, the bridge is also being fitted with state-of-the-art smart bridge monitoring systems, which should give early warning of any problems. This constant feedback of information is a feature of modern bridge design. As bridges perform ever more daring balancing acts, engineers need to know how well they're performing in order to avert possible disaster. This is the tallest bridge in the world, the Millau Viaduct in the south of France. Its tallest tower is almost as high as the Empire State Building. Compared to the simple steel structure of the old I-35, this is light years ahead in terms of bridge evolution. The Millau Viaduct is 3 kilometers long and uses what's known as a cable stay design, in which the weight of the bridge deck is distributed by cables across 7 towers. At this height and length, the bridge is constantly moving, so there are sensors in the pylons, the deck, the cables and the masts to monitor the movement of the viaduct day and night. Millau is the ultimate in the new breed of smart bridges, a living, intelligent, self-regulating structure. Both outside and inside, the viaduct is fitted with its own life support system. It's got its own electricity supply and its own water reservoir and fire hydrants. Should a fire break out on the bridge, firefighters won't have to pump low-pressure water from the town below. The bridge has its own weather station to warn of incoming storms and high winds, and it has an electronic nervous system which constantly reports on the health of the bridge. Thierry Vaissade is in charge of ensuring that all the movements and fluctuations of the bridge stay within safe limits.
Le viaduc il est construit, il est terminé. On pourrait croire qu'il est figé, mais c'est loin d'être le cas. En fait, il est en permanence en mouvement. Et nous sommes là pour vérifier ces mouvements et vérifier qu'ils vivent correctement.
There's so much movement in the bridge's enormous span that the metal road deck can't be permanently anchored to the cliff top. It has to be allowed to slide backwards and forwards over a concrete base.
Donc nous nous trouvons dans le tablier du viaduc de Millau. Au-dessus, vous pouvez entendre le trafic. Le tablier, c'est la partie métallique. Cette partie-là bouge, elle est fixée, elle est posée sur la partie fixe, c'est-à-dire la culée nord, où nous nous trouvons. Quand les températures augmentent, le tablier se dilate, il a tendance à augmenter. Quand les températures baissent, il se contracte et il va avoir tendance à repartir. Donc il faut savoir qu'on peut avoir une amplitude maximum de 80 cm, qui est représentée sur cette règle, donc 80 cm, avec 20 cm de marge de part et d'autre, au cas où. Aujourd'hui, nous sommes sur une journée estivale, donc on peut avoir entre 20 et 30 cm de variation sur la journée.
The instruments inside the structure have to accommodate the movement of the deck.
Le chemin de câble, il est monté sur un support flexible qui permet d'absorber justement ces variations. Par ce chemin de câble passent toutes les alimentations électriques, ce qui nous permet de voir vivre le viaduc au quotidien.
Bridge building has come a long way since the days of steel deck truss bridges. Millau has pushed the boundaries of what's possible. At Millau, they actually slid the deck out across the valley because it was considered too dangerous to lift it from the ground. Now that it's finished and has become an iconic symbol of French engineering, nothing can be left to chance.
Ici, nous nous trouvons au PC de surveillance du viaduc de Millau. Donc là, c'est le cœur du système. C'est ce qui nous permet de voir l'évolution du viaduc au quotidien.
From here, the maintenance team can monitor temperature, wind speed, humidity, and all the stresses and strains imposed on the bridge.
Dès qu'il y a un problème, quel qu'il soit sur le viaduc, ça passe au rouge et il y a un signal sonore qui retentit sur le PC et l'information arrive en clair au niveau du bandeau des alarmes.
Millau is a state-of-the-art bridge monitored against any eventuality, but it can still fall prey to the elements. If the wind gets stronger than 140 kilometers per hour, the bridge has to be closed for safety. In Hong Kong, the engineers at Stonecutters have to build for even stronger winds, typhoons. And wind is one of the biggest threats to bridges, as was witnessed in 1940 when the world's third largest suspension bridge was brought spectacularly crashing down. Bridges are always at the mercy of the elements. They expand and contract with temperature. They are corroded by rainwater and buffeted by wind. And as bridges try to span ever longer distances, the power of the wind becomes ever more lethal. The catastrophic effect of wind on bridges was dramatically demonstrated at Tacoma Narrows in Washington State, USA.
Last July, the nation hailed the opening of the new $6.5 million Tacoma Narrows Bridge over Puget Sound.
When the Tacoma Narrows Bridge was opened on July the 1st, 1940, it was the third longest suspension bridge in the world. It was a majestic example of the fashion for ever more elegant and slender designs. When the bridge started to sway, people thought there was nothing to worry about. And it remained open to traffic, earning the nickname Galloping Gertie. But 4 months after it opened, high winds slammed into the bridge, setting up a fatal oscillation.
As the great roadway, like a pendulum of doom, swayed and twisted in its death agony.
The bridge then spectacularly collapsed.
There it goes!
Just moments after it was closed to traffic. Incredibly, no one was killed, but the designers of the bridge had clearly made a drastic miscalculation.
Suspension bridges in the 1930s had thinner and thinner decks, a succession of bridges where you had success, success, then you go a little lighter, you go a little lighter, and then bingo, it fails.
It was later revealed that this marvel of modern engineering had failed because insufficient attention had been paid to aerodynamics. The solid steel plates on the side of the roadway had offered too much resistance to the wind. The Tacoma Narrows Bridge collapse is not only the most famous bridge disaster in history, but also the most influential. Since the Tacoma disaster, all suspension bridges and cable-stay bridges are designed aerodynamically with the aid of wind tunnel tests. Aerodynamics is the study of air movement around objects, and this knowledge grew with the rise of the aviation industry in the 20th century. Nowhere is this knowledge more important than at the massive Stonecutters Bridge, currently under construction in Hong Kong. This landmark $350 million structure will be one of the longest cable-stay bridges ever built, and it sits in a particularly complex and challenging aerodynamic environment.
Hong Kong is quite hilly, the new territories to the north. but to the south, it's actually open fetch across the ocean. So we've actually designed this bridge taking into account two wind loadings. One is when the wind is coming from the south during the summer and it's smooth and less turbulence, but also when the wind is coming from the north. The wind is far more turbulent because it's got to come over the hills, as you see, to the north there.
But most of all, they have to model the bridge to withstand the full force of typhoons, which can reach up to 200 kilometers an hour and bring widespread destruction to the region. At Stonecutters, they had to go back to first principles and test the structure in different laboratories around the world. There were 12 rounds of wind tunnel tests in Australia, Canada, China and Denmark, examining the aerodynamics of the deck, the cables and the towers. The towers at Stonecutters are 300 meters high, as tall as some of the biggest skyscrapers in Hong Kong. Climbing the towers requires 2 construction elevators and takes around 30 minutes. Because the towers are so tall, they'll be particularly vulnerable to typhoon winds. To help combat this, at the top of each tower a huge pendulum will be installed, a device known as a tuned mass damper.
Later on, we are going to cast a slab and then install a tuned mass damper at this part of the tower in order to stop vibration due to wind.
As the tower sways in one direction, the pendulum sways in the opposite direction to stabilize the structure. The main span at Stonecutters will be over 1 kilometer long. This makes it extremely flexible and vulnerable to the wind. Like most modern bridges, the deck is made of hollow steel box girders. Here, they're shaped like aeroplane wings for extra stability. The span also has a unique twin deck design joined by cross girders with a central air gap.
We have a very wide central air gap in this position. Now, this streamlined deck and the central air gap would make the Stonecutters bridge deck extremely stable against flutter instability, for example. But this central air gap also has a drawback.
The drawback is that while the air gap offers structural stability, it can also create a turbulent vortex of air which hits the downwind deck and causes the whole span to vibrate vertically. A similar problem was encountered in Denmark in 1998. This time the bridge was already constructed and started to display dramatic oscillations even in light winds. The design for the Storebælt Bridge had been tested in wind tunnels, but it was later discovered that at a scale of just 1 to 80, the models were not giving useful information. The problem is that complex aerodynamic phenomena aren't always reproduced in scale model testing, and you can't put the whole bridge into a wind tunnel. Stonecutters learned from the Danish experience and used a much bigger scale model of 1 to 20. The tests showed the likelihood of similar problems with vertical vibration. The solution at Stonecutters was the same as in Denmark. Guide vanes, or metal strips, were added to funnel the airflow around the nearside deck and break the rhythm of the turbulence.
We actually modified the shape of the deck to make it more aerodynamically favorable, and we introduced a pair of guide vanes to suppress the vibration problem.
Stonecutters will be held up by 224 stay cables, which will also be subject to complex aerodynamic forces. All cable stay bridges produce turbulence because of the way they cut through the air. So the cables also had to be tested in wind tunnels to see how they would perform. Studies have shown that wind and rain combine on the surface of stay cables to create water rivulets which run down the cable and alter the way the cable behaves. And it's not necessarily the strongest gusts or the heaviest downpours which cause most problems. Doris Yao is the stay cable expert at Stonecutters.
When there is rain and it is of medium intensity, and when the wind is not too strong, the rainwater will form a water rivulet on the upper surface of the cable, and the water rivulet actually changes the shape of the stay cables, and in the long run it may even lead to a complete failure of the stay cables itself.
The cables are made of galvanized steel wires which are protected against the elements by a dual layer of high-density polyethylene. It was discovered that a dimpled pattern on the cable's protective skin could counteract the effect of water rivulets by breaking up the flow.
We are confident that by installing the dimples on the cable surface, the rain-wind-induced vibration could be mitigated.
One way to make the bridge less vulnerable to the wind would be to shorten the span by building towers in the water. But that would expose the bridge to a whole new kind of risk, being smashed into by any of the giant container ships that pass beneath it.
Ship impact is a serious design situation for bridges, and there have been a number of collapses of bridges in the past due to ships colliding with bridge piers, particularly in the States. One of the most notable was the collapse of the Sunshine Skyway Bridge in Florida in 1980.
To all stations, this is United States Coast Guard, St. Petersburg, Florida. The vessel, Some Adventure, 606 foot, has hit the Skyway Bridge.
In 1980, the southbound span of the Sunshine Skyway Bridge in Florida was destroyed when a freighter collided with one of the bridge's piers during a storm. The impact sent over 400 meters of the bridge plummeting into Tampa Bay and caused 6 cars and a Greyhound bus to fall 50 meters, killing 35 people.
Any vessels in Tampa Bay area, Skyway vicinity, proceed and assist. There are reports of people in the water.
One man survived the fall when his pickup truck landed on the deck of the Summit Venture before falling into the bay.
I seen the ship and I figured it was all over when I couldn't stop. The next thing was I was in the water and I managed to get the door open and I started swimming to the surface and I finally made it up. And I got a lot of water and there was a piece of the bridge there and I held on to that.
That tragic event really marked a major turning point in people's understanding of the seriousness and the consequences of ship impact.
Positioned at the entrance to the world's busiest container port, stonecutters will be very vulnerable to ship impact. Towers in the water were therefore ruled out. Instead, the designers proposed to support the bridge from the quayside, but they needed to be sure this would be safe. Matt's team studied the movement of traffic in the Kwai Chung container port and carried out a statistical analysis of the likelihood of a ship colliding with the quay wall.
We found that the chance of that was maybe 1 in 300 years, which is too frequent for us to accept without some further study.
Further tests were carried out to model the effect of a ship impact on the foundations of the towers. Such an impact would drive a giant bulb of pressure through the soil, right into the base of the structure.
The impact scenario that we investigated was a 155,000 deadweight ton vessel traveling at 6 knots. That's equivalent to the largest container vessel in the world, traveling at about the same speed as the ship behind us is traveling.
So the team at Stonecutters added extra reinforcement to the top of the foundation piles to give them enough strength to resist that pressure bulb during ship impact.
So we can say with confidence that should one of these super container ships collide with the quay wall, then Stonecutters Bridge would stay standing.
But it's not ships or wind or corrosion which is the biggest destroyer of bridges. The most hazardous time for a bridge is when it's being built. In 1970, the Westgate Bridge in Melbourne collapsed during construction, killing 35 workers.
It fell from a height of 150 feet. According to eyewitnesses, the section of the bridge broke its back along a central seam. There was virtually no warning for the men working inside.
The tragedy occurred when 2 box girders were being connected. The box girders were out of alignment by 4.5 inches, and an attempt was made to force one of the girders into position using 80 tons of concrete blocks. When the blocks were removed, the whole span snapped. The construction of any bridge is always a risky business. Engineers are working with heavy loads at great height, and there's always a battle against the elements and the law of gravity. At Stonecutters, there's the extra hazard of working over a busy shipping lane.
Kwai Chung Container Terminal is one of the busiest container ports in the world, and one of the key safety issues for us has been ensuring that we can erect the deck of Stonecutters over the navigation channel without endangering either the shipping or the workers themselves.
The cargo traffic coming in and out of Hong Kong is too important to stop while construction is going on. So during the lift of sections of the deck, a safe working zone is set up, 200 meters by 200 meters, which is patrolled by security boats. The deck sections are constructed in China and delivered to the site by barge. A new 300-ton section is lifted into place by 2 giant lifting frames every 2 weeks.
That means 8:45 we can move out the barge, is that correct?
In charge of the lift is Operations Manager Patrick Chan. Coordinating from above is Englishman Nigel Day.
Okay, you all set?
Two 300-ton cranes lower their clamps into place. The barge has to be stabilized in the water using GPS-controlled motors at each corner. If it were to drift into the shipping lanes, the results would be catastrophic.
Okay, Jackie, what pressure have you got?
Each step of the process is coordinated with great care and concern for safety. Any problems, and the process is halted.
On, and let me load. Then we load down the spreader beam.
The barge also has to be completely static, so that when the bridge section starts to lift, it doesn't twist on the cables. As they're lifted, the deck sections sag and distort under their own weight. What this means is that at the end of the 30-minute lift, the box girders have to be bent back into shape to fit the rest of the deck.
Okay, what's the gantry room? Okay, I'm going to start pulling in 2 minutes.
Once the deck section is level, it's pulled towards the rest of the bridge. The outer edge girders are then forced back into shape using an external post-tensioning system, shaped like a set of goalposts and fitted with 4 500-ton hydraulic jacks. Potentially, it's a similar situation to Westgate in Melbourne, where the bending of box girders caused a fatal collapse of the structure.
Okay, boys, after 3. Yan, Yi, Sam, pull.
The difference at Stonecutters is that every stage has been modelled by computer, and there's close monitoring of the shifting geometries of the structure and the stresses being imposed on it throughout the operation. The bridge builders have learnt from the mistakes of the past and make it look easy.
When you've done that, have a break. Lunchtime, okay? So we're going to take a lunch? Yep. Okay, good job. Good job, yep.
Nonetheless, when the bridge is only half built, it seems to hang precariously in thin air.
The bridge is not precarious at all. One of the key areas that we considered was when the bridge was cantilevering out over the Rambler Channel. We are focusing very much on the stability and the safety of all workers on the bridge deck at all times during construction. A lot of instruments have been put in to interrogate the performance of the structure during the construction process. After every lift of every segment and installation of every set of cables, we have analysed the structure.
After every lift, the new deck section is threaded with cables and connected to the tower. The cables arrive from the factory on giant reels and are straightened out on the deck before being lifted by crane up to the stainless steel tower top. They're too heavy to be manipulated by hand, so they're manoeuvred into place by jacks. A matching cable is then attached to the backspan so that the extending deck is perfectly supported. Lessons learned from previous bridge failures during construction mean that Stonecutters is completely stable throughout the process. Step by step, this super bridge reaches out to meet its other half across the channel. Stonecutters will be a state-of-the-art bridge representing the pinnacle of engineering achievement. But it's actually just a tiny part of an even more ambitious project. Stonecutters will be just one link in a huge infrastructure chain which will culminate in a monster 40-kilometre bridge connecting Hong Kong to Macau. When bridges collapse, the images travel around the world and live long in the memory. Shocking bridge failures damage our faith in man-made structures. But bridges are now spanning previously unimaginable distances in ever more ingenious ways. They're crossing oceans and connecting countries. In Hong Kong, there are plans to build a 40-kilometre super bridge to Macau, which will test bridge building to new limits. Construction on this super bridge is scheduled to begin in 2010. It'll be built from a body of knowledge amassed from all previous bridge failures. It'll be designed to be disaster-proof.
There is increasing ambition in design, but safety is always first. We have to make sure that our bridges are strong enough to withstand all of the design loads. So I don't think that increased ambition is being achieved by reducing the margin of safety. It's more by pushing back the boundaries of imagination.
The philosophy at Stonecutters is, if it can be imagined, it can be built, but built safely. In Minneapolis, they've been working round the clock to build a new bridge on Interstate 35 to replace the one which collapsed in 2007. Valuable lessons have been learned, and this time it'll be a much safer bridge. A bridge built from disaster.
Obviously, the events were very tragic, but I think bridges are becoming more safe. We know a lot more about bridge behavior than we did 75 years ago, 50 years ago. I think we're applying these technologies now, like the health monitoring system or the redundant aspects. We're aware of these things, and all these new bridges now incorporate this new technology.
Up to 600 workers have been employed in the new bridge at any one time, including one of the survivors of the 2007 collapse.
That's what I do, so I worked on the new bridge for 6 months and back doing repair, working on bridges.
But not all of Jeff's colleagues have regained their nerve.
Some of them are still not back to work yet.
The eyes of the world are on the new I-35 bridge, and it has to be seen to be super safe. For that reason, the designers have been extra cautious. Even though the bridge has been designed to carry 7 lanes of traffic in each direction, it'll only be striped for 5.
I mean, not only have we built it very quickly, we've built it with more quality oversight, probably by a factor of 10, than I've ever seen on a job.
In the early hours of the 18th of September 2008, the new I-35 bridge across the Mississippi River opened to traffic an incredible 3 months ahead of schedule. The bridge builders have used state-of-the-art smart bridge systems to ensure that a repeat of the previous year's collapse never happens again.
Well, there's thousands and thousands of bridges across the nation and across the world, and people have to have confidence when they use that public infrastructure that they're going to be safe when they do it.
It's been estimated that the USA needs to spend $1.6 trillion on its infrastructure in the coming years. Minneapolis has been a wake-up call. In Hong Kong, the ambition to build futuristic infrastructure is balanced by an understanding of the need to constantly maintain it.
Building infrastructure is only part of the story, and only a small part of the story at that.
The bigger story is that in the age of super bridges, it's no longer enough to create a magnificent structure. You have to be equally inventive to protect it from disaster. It may be impossible to design a bridge that can withstand every threat, but as massive spans link communities all around the globe, the lessons of past mistakes are being learnt and are helping shape the future.